All right. Hello, my name is Caleb DeRocha, and I'm going to do my presentation on the linear regression of TZ Aurigae. That's how I pronounce Aurigae anyway. So how you would spell it is Aurigae. That's the classical Latin pronunciation, and then obviously the TZ in front. That could be a tau zeta, but I'm just going to pronounce it TZ Aurigae because that's the best way I can figure out how to pronounce it. There isn't really anything I could find online that would help me otherwise. But for the most part, let's just keep it as this. I'm not going to be sharing my video, unfortunately, because I'm in the process of changing rooms with my dad, and there's a lot of trash, not trash, but just stuff in my background. That being said, there will also be probably some background noise since I am home and my family is currently watching TV and doing some stuff while I'm doing this. So, just a bit of disclaimer that my apologies if it's this presentation isn't as formal as it could be. So, anyway, without further ado, here's my stuff. So first, I did the photometry of the TZ Aurigae. So basically, if we look at the AA VSO chart, this in the center is TZ Aurigae. I'm just going to pronounce it like say TZ because I am I kind of want to get this submitted as soon as possible so that I can get to my other homework. So as you can see, there's other stars here with numbers next to them. These numbers are the brightnesses of those stars. So say this is 125, that's 12.5 and 11.3 here. The reason why that they don't do the measurement of the star with a decimal place is because you could easily mistake it for like a small star like this. So it just makes it easier for the viewer to realize, oh, that's not a decimal place. That's a star, or oh, that's not a star. That's a decimal place, I should say. So yeah. So I did just normal photometry, which is basically just taking this brightness and measuring with against like say brightness of this star, or in this case I did this star. Um, so that's normal photometry. Ensemble photometry, which is what I originally planned to do, was with these like all the stars in the field of view, just averaging their brightnesses out and then comparing that to um, TZ. Of course, both work just as easily and just as well, although the ensemble photometry typically is a lot better when it comes to measuring the brightness because there's less error in the measurement since you are doing an average. So this graph here of TZ would be a lot nicer. It's already really nice as it is, but it would be a lot nicer. So as you may notice, this brightness is actually in magnitudes and that the numbers are actually going down as you go up the graph, which seems kind of backwards, but that's actually how the magnitude scale works. Um, so as you can see with TZ Aurigae, it basically goes up in brightness just over 1 magnitude, which is huge. That is a huge difference in brightness. I think 6 times as bright as it was originally down here. I could be wrong with that number, but it's a lot brighter, essentially. Probably isn't 6 times brighter, but it's definitely brighter. Essentially, it's a big jump, and we're able to find this jump due to the fact that we know the measurement of magnitude of this reference star, the orange, right here. And then we have these check stars to compare it to. These check stars, yes, there is some noise, but that is expected since we're on Earth. The atmosphere does refract the light a lot, so it makes it difficult for us to really keep it consistent with the brightness. In fact, you're probably never going to get it that consistent unless it's a perfect night with perfect conditions, which um, you can't always get. That's either rare or impossible, especially in Bridgewater, which is actually where the data here was taken from. So these brightnesses come from the graph, as you see behind. I mean the spreadsheet that you see behind the graph. So we're measuring the magnitude over time. The timestamps are in Julian date timestamps. So essentially, what we're doing is showing the brightness over time. I kind of forgot where my train of thought was going, but essentially, we're just uh, doing that and doing something like that in Bridgewater, where it's never really perfect weather conditions year round, and we're not exactly that high up above sea level. We're bound to get some atmospheric shifting of the light. Well, not shifting, atmospheric. I forget the word. There's a word for it, but atmospheric um, wiggle of the light, I guess. That's a good way to describe it, though. It kind of just makes the star look like it's wobbling. So normally I would do ensemble photometry, which is one of the main things I like to do, which would take these brightnesses of each of these stars and make it sort of average them out into being one star, one virtual star, basically. And then we would measure it against this graph of TZ. It would look a lot nicer, but I didn't have the time to do that. My apologies. My cat is meowing at my door. Hold on a second. What? My apologies. So essentially, that's the photometry part of the experiment. And then using this data and also collecting averages for all of these things, I was able to come out with linear regression based on this paper that I found on linear regression. So technically, this is ensemble photometry in some way or form. My cat's like all over me right now, and essentially, it just explains how to code or like set up an ensemble photometry table in Excel so that amateur astronomers who use photometry could do this so that they can figure out whether a star is variable. For this, I made sure in the linear regression, like the first one, that I did not include TZ in my data in the regression, because otherwise it would have been a little weird. We wouldn't have this perfect, almost perfect linear line, essentially, when comparing the expected magnitude with the magnitude that we actually get. So, because we get this near perfect line and an arc squared of 1, we can pretty much assume that this is a very, very, very good like field of view that we've picked and stars that we've picked in said field of view. And essentially that means all the stars are of a consistent brightness within the degree of tolerance that we need, that we would like to see. However, the main reason for this project is to essentially use this in other fields of view, or find ways to use it in other fields of view. I would want to try to find other ways to do it in other fields of view so that I could find out which stars are consistent and which ones aren't, and just go from there. My apologies, my cat is distracting me right now. She's just, yeah, no. Anyway, so in the linear regression with the object, or with TZ, I added the average beginning magnitude for this because there wasn't actually, if you look in the AAVSO variable star plotter for TZ Aurigae, there is no indication of the brightness that you would get. Hello. So because of that, I just took the average of, well, roughly the average of the beginning, like first 10 to 20 um, um, time, like measurements over time, like timestamps, I should say, of TZ, and then I just put in the average for the as the expected magnitude, because I had to work with something. From there, I was able to compare it to this, the actual magnitude based on the average object right here. So that is what you see here. And then from that, I graphed it out. And as you can see, what was once a perfect, near perfect linear regression here has now sort of gone a little off. And this is the particular one that's TZ. And as you can see, it's completely off from the rest of it. And that gives us an R squared of 0.9725, which is not as, which isn't terrible, but it's definitely not something you would want for like a variation in brightness of a star that you wanted to use as something that was consistent. So from there, we can, as you would expect, TZ is a variable star, which is very well known. It's been known for over 100 years. But this basically just gives us an example of how it could be used in ensemble photometry, particularly for something that I would want to apply to is exoplanets. So through something called the transit method, which is basically, say you have a star, and then you have a planet going in front of that star. That's not the best. So star, planet going in front of the star. Over time, the brightness of that goes down and then comes back up. And this dip, we can measure that brightness dip, and essentially we can figure out, oh, there's a planet there. What I want to do is be able to use this in ensemble photometry and try to figure out a way to implement it into fields of view that are not as well known, with candidate exoplanets, hopefully, and be able to figure out a way to um, find stars that aren't variable through, or are variable through this method of linear regression. Um, I wasn't able to get too much into the details this semester since this was probably my busiest semester in all my time here at Bridgewater. But um, my hope is in the future to be able to think through how I would implement this into ensemble photometry for exoplanets and how, sorry about that, um, how I'd be able to implement it into ensemble photometry for exoplanets, and also how I would be able to use that data, use that information to um, like throughout like a longer period of time to essentially either confirm or like not confirm uh, the consistency of a brightness of a star or a few stars. Um, so yeah, that's essentially it. I am very sorry about all the background noise and the fact that I couldn't show my video. But this is something that um, I've always been passionate about. Just photometry, exoplanets, all this stuff. I find the linear regression thing a very useful tool when it comes to photometry, and I am definitely going to think of ways in the future of using this in any future projects that I do, and like trying to figure out the variability of stars in a field of view that is unknown. So yeah, um, thank you for coming to my presentation, and I hope you have a great day.